Hello, and welcome to an example of solving a differential equation. I wanted to do another exact equation for you, so I've gone to our textbook, page 73, and I picked problem 40. And I've written the problem down already, and well, it's a long one, isn't it? But it's not really difficult, but it involves a lot of the trig functions, and so we may have to think a minute or two about how to differentiate and integrate the trig functions. Don't forget, you can have tools like a table of integrals, a table of derivatives. If really stuck, you can use Wolfram Alpha. Many of your graphing calculators will remind you of what the derivative of tan is, or the integral of secant square. So you've got lots of help, and you can also use notes, and I still suggest that you use note cards and create a deck of note cards for yourself as you go through this course, and that technique would be useful in many other courses that you take as well. Well, this is an equation, and it's written in the form of an exact equation, isn't it? Where I've got it in the differential form, a dx function out here, function of both x and y, and a function here also of x and y. And traditionally, this is the function that we would call m of x, y. And this is the function we would call n of x, y. And to see if this equation is in fact exact, we need to look at the partial of m with respect to x, y. The partial, of course, the partial taken with respect to y. And then we'll need to take the partial of n with respect to x and see if they're in fact the same. So let's just take the partial of m with respect to y. So here's m, and if I take the derivative with respect to y, then this is just the coefficient, so that's just an e to the x coefficient, and the derivative of sine y with respect to y would be cosine y, and I'm taking the derivative with respect to y, so the derivative of tan x would be secant squared x. So there's the derivative of m with respect to y. Now let's try the derivative of n with respect to x. And here's my n function. The derivative of n with respect to x would be, well, the cosine y would be the coefficient, but the derivative of e to the x would just be e to the x. So e to the x cosine y plus, and now I'd have to take the derivative of secant squared y, but with respect to x. And so with respect to x, secant squared all right, I knew that there was something wrong whenever I was trying to take the derivative of n with respect to x. And what was wrong was, when I wrote the problem down for you originally, this red x right here, I had forgotten the x. And so now I've added the x back in. It has no effect upon taking the derivative of m with respect to y. But when I get down to the derivative of n with respect to x, we'll just kind of talk through that again. It's going to be cosine y as a coefficient, and then the derivative of e to the x with respect to x is e to the x. And the second term here would be secant squared y. That's just like a coefficient because I'm taking the derivative with respect to x, and the derivative of the x term would be 1. So this would be a secant squared y. So here's the derivative of m with respect to y and n with respect to x. And if I examine the two, I see that they are in fact the same, and this is in fact an exact equation. So that's good news. And why is that good news? Well, that's good news because I know how to solve an exact equation. So first of all, we're going to find f of x, y. When we say that the equation that we started with was an exact equation, we mean that there exists an equation in x and y whose derivative is exactly the equation we're trying to solve. And so f of xy equal a constant would be a solution to the differential equation. So as soon as we find f of xy, well, in fact, we're done. Now, if the equation is exact, we know that the partial of f with respect to x is what the m function is. So I guess I'll write that down for you. We know the partial of f with respect to x is indeed what the m function is. I'm really abbreviating here. Therefore, f is equal to the integral of m dx and plus some function of y alone. This is almost like a constant of integration, but where do we get it? If I differentiate f with respect to x, any piece of f that was a function of y alone is going to be 0 when I differentiate with respect to x. And so in order to find f, I will integrate m, but I'll also have to recover this g of y. But we'll be patient, and I think we'll be able to do that. So f of xy is going to be equal to the integral, and I'm just going to write down what m was. You may remember, or we could scroll up, but this was sine y plus tan y, and then I'm integrating with respect to x. Let me box these things in a little bit just for form, and then plus a function of y alone. All right, so that's going to be f, and now just evaluate this integral. So this is just a sum, so the integral of the sum is the sum of the integrals, and I'm integrating with respect to x, so this is going to be sine y times the integral of e to the x dx, which is, that's our easiest integral, and this would be e to the x sine y. Now we've got one more here, tan y, but I'm integrating with respect to x. So tan y with respect to x would just be tan y, and so this is the integral dx, which would be x tan y, and then plus a function of y alone. And put a little dot in there. Okay, well, that looks right. So, well, you think mission accomplished? We know f of xy. Well, mission almost accomplished, but not quite, because I don't know this g of y yet. So I need to find g of y as my next step. Well, we've got a shot at finding g of y, because I know that since the equation is exact, the partial of f with respect to y is equal to n of xy. So if I would take f, and here's f, this expression is f, and differentiate it with respect to y, I would have n. Now, n is a long expression, so for right now, I'm just going to write this as n xy. We'll replace that in just a minute. Would be equal to, now take the derivative of f with respect to y, the derivative of f with respect to y. So this is going to be, I'm differentiating with respect to y. So e to the x is like a coefficient, but the derivative of sine y would be cosine y. And then I'm differentiating with respect to y, so x is like our coefficient, so it's an x. And what's the derivative of tan y? Would be secant squared y. And I'm differentiating with respect to y, so I've got a function g of y alone. That would be then g prime of y. Now, you might think, well, we didn't do ourselves much good there because I've still got a function of y, a g function of y that I don't know, and now I've got its derivative in here. But this is a differential equation, and we're all about solving differential equations. And so let's rewrite this, replacing n of xy with what it really is. So when I rewrite that, and I think I'll just go ahead and scroll right now. So when I rewrite this piece, I get e to the x cosine y plus x secant squared y equals, now this is n of xy, that's what this is, equals, and now I'm going to write the right hand side down here, e to the x cosine y plus x secant squared y plus g prime of y. Now we're going to simplify that, and this one simplifies mightily. Here I've got an e to the x cosine y on the left and an e to the x cosine y on the right, and so those two are they're going to add out. And I've got an x secant squared y on the left and an x secant squared y on the right, and so those two are going to add out. And we're left with g prime y equals 0. Now what does that tell you about g? That tells me that g of y must have been a constant. So now I know f of xy, and let me point out, here's f of xy. We can scroll that up just a little bit. There's f of xy, and here's its expression, and now I know g of y. So finally I can write f of xy is equal to, we'll take it up right here, e to the x sine y plus x tan y plus g of y. G of y is just a constant, so plus a constant c. And what have we done? We found f of xy. So we've solved the problem. Well, congratulations to us. And we'll have another video very, very shortly that will take us through the reducible second order equations. And I will just tell you more about that in the introduction to that video, but thank you.